All right. Okay. Well, hello everyone. I'm going to turn over the reins in a second, hopefully. But I wanted to finish up the lecture last time talking about this last little bit of optimization, which is actually, in some sense, the most important for a lot of this class because it's what you're going to actually use to solve these problems on the homework. It's also a very good technique to know in general. Before I start, though, were there any questions from last time, having let the sort of dust all settle regarding optimization as a whole? Were there any questions? Okay, well, we have the office hours. They're all posted. Haven't seen many people yet, but I guess it'll change when the first homework comes out, I'm sure, which is on Wednesday. So we will certainly expect a little bit of an uptick. All right, so what I'm going to talk about just for a few minutes now before turning over the lecture to going back to search is this last little bit on how we solve optimization problems in practice. So I told you a lot before, both about forming optimization problems, how do you build these things, and then how do you kind of solve them in, algorithmically in theory, right? And we had algorithms like gradient descent or Newton's method, and then we had, I think, even this fairly complex barrier method before. This is actually a pretty complex algorithm here that essentially puts these penalty functions on inequality constraints, and you essentially solve sort of more and more tighter versions of these problems. And as this scale here, t goes to 0, you approach the real problem. But it sounds a little bit tricky, right? Because you might run into numerical precision issues when you start having something that is, almost 0. Basically, this thing is infinity if it's negative, and it's almost 0 if it's positive. So there are issues, and these things are hard. And the good news is that in this class, we're not going to worry about the numerics of actually implementing these things. It really is quite tricky. Getting it right takes, a lot of work and there's whole classes on this thing, so we're not going to worry about it too much here. What we're going to do here is talk about ways that people actually solve these in practice. And I should say this includes myself. So when I solve problems like this, I solve optimization problems all the time. I almost never, until I've already worked out a model in a lot of detail, I will almost never write code from scratch to solve the actual problem itself. Instead, what I'll do is I'll use a freely available library to solve these things, maybe in small cases first, make sure the technique actually works as a whole, and then only if absolutely necessary will I go on and then actually write some specific code for it. So the good news here is that there are, for many types of optimization problems, including most of the ones we covered before, there are very mature, very well-developed pieces of code that can take these things in pretty general forms and solve them for you. All right, and so this means, I should even say, it goes beyond just kind of what there was 10 years ago, where you had to put a problem in a certain form. There are now very powerful, almost modeling languages, where you can actually describe problems in very natural ways, and the library will do kind of all the hard work. And getting familiar with these things is an incredibly useful sort of set of skills to develop. Some of the more well-known libraries of this form, there's one called CVX and YALMIP. These are both libraries for MATLAB. Actually, by show of hands, who here has heard of either of these before? Who here has used either of these before? Okay, so not too many. That's actually good, because it'll be a new learning experience for everyone. There's also something called AMPLE and GAMS. These are more kind of OR types. So has anyone used either of these? AMPLE or GAMS? I'd be surprised at that. Okay, someone. Wow, all right. Those are a little more esoteric, at least in computer science. They're much more used in a lot of engineering disciplines, but they're a little bit more esoteric here. What these let you do, and we won't use these ones, mainly because we're going to be using Python rather than MATLAB or Octave for this course, but what these do, and what we're going to use does, is let you specify problems kind of the way you would write them. That's the goal. So when you write them, you don't think of a function in terms of its gradients and its Hessian, these kind of things. You just write the function. These libraries let you just write optimization problems kind of almost exactly as you write them down in a paper. And then we'll do all the hard work to convert that to kind of a standard form and apply known solvers all very nicely. The one we're going to use is a relative newcomer to the group. It's called CVX Pi. It's by the same group that does CVX, or at least has the same original offshoots as the group that does CVX. This is Stephen Boyd's group at Stanford University. And he actually was one of the 2 authors on the book on convex optimization, so you may come across his name other times. This is a Python library for specifying and solving convex problems. And it's not as full-featured as other ones, but for what we're doing in this course, it is more than enough. And it works in Python, which is what we're going to be using for this course. So that's why we're using it. Having said that, this is very much alpha software. This is under constant development. The main page for this software, as you can tell, is a GitHub repository. That means it is under active development right now. Well, I guess ideally it means that. So what we're going to do is, and frankly, because of this, you're all going to be kind of test subjects in a way, because this is early stage software. However, I think it is mature enough to the point where you will actually be able to use it, and it will make your lives a lot easier. It's still early, but it will make your lives much, much easier than trying to write any of this stuff yourself. And I'll show you an example of that in a second. So what we're going to have is for the first homework, there will be one problem that will involve CVX Pi. What we will have when we release it on Wednesday is a page on the website that shows how to install this for different operating systems. But even that, I mean, this is source you have to download, so there could be some problems there. And so please start that early and let us know if you have problems, because this is a prerequisite for solving the homework problem, not the problem itself. Right? Installing the software is a prerequisite. And we should have instructions for both, for Linux or any Unix really, but I think really just Linux, Mac, and Windows. We should have instructions for all of those. So let me now just finish by showing you how this works. So let's talk about this a constrained version of this Weber point problem, which I talked about before. Essentially, it is, we'll call it in 2 dimensions right now. You have a bunch of points, which I'm calling AI. You want to find the x that minimizes the distance to all those points, the sum of the distances to all those points. And not square distances, but just distances. Otherwise, it would just be the mean of them. But with distance, as we talked about before, it was harder to solve than that. We're also going to add a constraint. This constraint here says that x1 and x2 have to equal 0. So the x coordinate plus the y coordinate have to equal 0. There's no real reason for that. It just means that eventually the allowable points have to lie on a line, right? We're just enforcing that kind of arbitrarily here. But the point is, I want to show how these things are represented in a language like CVX Pi. Okay, so here's Python code to solve this problem in 3 lines of actual code. The rest is kind of just boilerplate generic stuff. But the important lines here are 3, and it really corresponds almost exactly to what I've written up there, which is what's really cool about this. Without doing this, this is really hard to solve, right? Without I shouldn't say hard, it's just really tedious using other techniques to go about solving a problem like this. These kind of modeling languages have made that just orders of magnitude easier. Let's go through this line by line. Again, we're assuming some familiar with Python here. If you don't have it, it's an incredibly easy language to learn. If you have other programming experience, it should not be hard at all. But this is going to be Python. I'm not going to dwell on the actual Python parts here. I'm just going to dwell on the content of the code itself. So first lines, this is just imports the relevant libraries. So I'm importing CVX Pi as CP just because I call it a lot. I'm just going to call it CP. The other one we're importing is this library called CVX opt. That is also a set of routines that we're really not using too much here. We're using them just for generating random variable or generating normal random variables. But it is a set of libraries that interfaces well with CVX Pi, and so it's actually useful to use that one as well. So we import these 2 things. Now I'm going to set up my problem. And so my problem is, remember, I have a bunch of points AI, where each AI is an R2. Okay? So I'm setting n, the dimension of x, to be equal to 2. Or sorry, the dimension of a to be equal to 2. M to be equal to 10. That's the number of points I have here, because it's going to be summing from I equals 1 to m. So n is 2, m is 10. And then I'm going to generate a matrix A that is just n by m. So what this is saying here is that, where's the chalk? Little ones here, I guess, is all that I have. They have a bigger one? I like the bigger ones, but I guess there's little stubs here. Okay, so that's basically making a matrix A. like this, right, with m equals 10 columns and n equals 2 rows. And each row here corresponds essentially to one of those points. Right? And this just means it has each entry is just random normal. We're just doing this that has no significance. It just is so that we can create some problem data. Right? In reality, you would actually get this from what your actual points were in the world that you cared about minimizing the distance to. All right, now is the part where we actually use this library here. So here, these three are the important lines. Or these four, I guess. The first thing is we're declaring x to be a variable. All right, x is the thing we're optimizing over. That means it's a variable. So here, x equals cp.variable n. This just means x is, we're calling cvx pi, making it a variable of size n. You can make the matrices too by passing two things here, but here we're just making it a vector. We're just making it a vector of size n. Okay, this next one is a little bit more, this is sort of the kind of the magic of the system. So again, how do we specify what we want to minimize here? Well, we want to minimize the sum of all those norms. Now this is sort of combining both something from Python and some of cvxPy, so hopefully people will be able to parse this okay. Everyone's familiar with list comprehensions in Python, or at least familiar with that concept. If you're not, this is what I'm doing here. So look them up, Google those, and see what's going on there. What I'm doing here is this thing in the brackets here is what's called a list comprehension. So it makes this term for all I in this range. So for I, basically 1 to m, or really 0 to m minus 1 here, depending on how you index things. It creates this term, which this term depends on I. So this term says it's the norm of x minus the ith column of A, which is just this thing, takes the norm of this and the 2 norm of that. The 2 norm is the Euclidean distance, and then forms a matrix of all of these things. Rather, a list of all of them, I should say, sorry. This thing becomes a list of all of those terms, and then we sum them together. So this line here corresponds to that objective exactly. And the nice thing about this is you can kind of, maybe modulo reading Python, you can kind of see pretty well that this corresponds exactly to that, right? You don't have to worry about kind of thinking about variable indices too much, or sort of specifying what's called a cont program, which is how you used to have to do these things. But it's really pretty intuitive, right? You just take all these things, you use a norm, that's exactly what you're minimizing there, and you form the sum of them. Similarly, the constraints are also pretty easy. The constraints is just the constraint equals the fact that the sum of this x, that's now actually the sum of the individual elements in x, equals 0. Also very easy, right? Finally, this is kind of the little boilerplate code again that we'll just call the problem. So you call the problem as cp.problem. cp.minimize f, you have to say if you're minimizing or maximizing it. If you try to maximize this function, it would tell you something's wrong because you can't maximize a convex function. That's not an allowable convex problem. You have to minimize them. You can maximize concave functions, not convex ones. So you pass just cp.minimize f and then the constraints, and then you call solve. And you print x.value, and that will print the solution to this thing. So it seems kind of easy here, and it really is pretty easy. But what's amazing here is how much work this would have taken even 10 years ago to write equivalent code to solve this. These are sort of a new set of techniques that builds upon kind of the scriptability of languages like Python or MATLAB, along with essentially code that can put problems like this through a set of rules into a very, basically it can apply rules to these things such that the standard solvers that are out there will understand them. And so we're not going to worry about kind of the back end of this. We're just going to use tools like this to actually solve problems that we care about. Now, at some point, probably if you want to sort of go further down this line of research, it probably will be good to figure out how these things work and how the code behind it really works and what it's doing, the machinery. But for our purposes, sort of the quick overview I gave last time is enough of that. And we're just going to talk about how you use the tools to actually solve the problems you want to solve. So, with that said, yes, what's the question?
Will it give an error if the function is not convex outside the constraint?
Yes, it will definitely, if you specify a non-convex set of constraints or a non-convex function, it will say this is not a convex. It'll give you some cryptic error maybe, but it basically means this is not a convex function. And by the way, you can't always do everything either, I should say. So if you try to say, instead of norm, so this says cp.norm of this thing, x minus whatever. Now the norm, remember, is just equal to, so the norm of x, the 2 norm of x, is just equal to the square root of x transpose x, right? Now, it is not that easy to verify this is convex by standard rules. So, for example, the square root is not a convex function, right? Square root is actually a concave function for x greater than 0. So if you just plug in cp.square root and then this thing squared or something like this, that actually might throw an error too. In fact, it will throw an error as well. Don't worry about that now. What this means actually is that the set of allowable functions here is actually a subset of all convex functions. It obeys certain programmatic rules that say we know if we combine functions in a certain way, they're convex. So it knows about norms, that norms are convex, but it can't figure out on its own that an x transpose x, the square root of that is the same as a norm. So try to, there's actually a very small set of rules. It's linked to on the website that describes that describes CVXPy, but you have to use kind of the right set of rules. Now, this class is not really about that in general, so if you have problems and think something should be working and it's just not, then come talk to TAs by all means, or TA or us, the instructors. The goal is not to make it hard for you to use, the goal is to make it easier for you to use these things. So it will throw errors. Usually it's because you do something wrong, but if you're doing something right like this and you just are sure you're doing it right, then come chat with us because it's meant to make life easier, not harder, these kind of things. All right, so that's all I'm going to say about optimization. That concludes our 2+ lecture on optimization. The big story, optimization is really, I would say, one of the most prominent trends in AI in the past 15 years. 15 years ago, the book sort of was first being written, and it didn't even make an appearance in the book. Sort of this kind of optimization, maybe it was there, but it was sort of very slightly mentioned. And now, if you go to an AI conference, there's optimization everywhere. Convex problems in particular are a small, granted very small, but useful subset of optimization as a whole. Because we can solve them efficiently, they still find a huge number of applications. And by the way, we have nice libraries that can sort of make our life very easy when it comes to solving them. Finally, as I said, maybe I kind of merged these 2 points, but there are a lot of ways you can solve these things. And sometimes you have to just go through all the hard mess. And in fact, a lot of what research involves is for very big problems or for very specialized problems, can you come up with faster algorithms to solve these things that are better than kind of if you just plug it into the generic code here. But for our purposes, a lot of small or medium-sized problems can be solved very quickly and very efficiently with these freely available libraries. And so with these tools, hopefully, and through doing the homework and such, you'll develop kind of a pretty good skill set to be able to solve these kind of problems and actually not just hypothetically, but actually write code that solves them. So with that, I'm going to turn it over, and we'll return to talking about search now. Actually, I should say, are there any questions first? OK, so with that, I will turn it over, and we'll keep talking about search. Yeah, just
Okay. Okay. All right, so we had a sort of a discontinuous session on search, unfortunately. And that was interrupted by travel. I apologize for that. But you got a great introduction to optimization in the continuous world. And now we're going to return back to doing search and some optimization in the discrete world. All right? So just to remind, we had talked about search. And we had done uninformed search, meaning that we weren't really using a lot of knowledge about the domain to guide the search. We were only using very local knowledge in how we generate the next steps in the search tree. And search trees, look, just using the simple 8 puzzle as an example, was this idea that you had this initial state and that you would transform that initial state through a set of moves that would give you a goal state. And the goal state, for example, you might want to get to is some idea where you go 1, 2, 3, 4, 5, 6, 7, 8 would be in this simple domain. And the types of moves you could do would be operators that you would apply would be like moving the space around, so that if you move the space to the left here, you'd get this board. If you move the state up, you'd get this board. If you move the space to the right, you'd get that board. And that's how you would generate the next states. And through these transformations, you'd go through various plies of the different boards until you would find a solution, given whatever your goal state was. So that's what we did. And we had these very uninformed methods, depth first, breadth first, iterative deepening. And all these things could find solutions, but given certain constraints, but they weren't very efficient. And you can imagine that even in this case, as I think was pointed out in last class, if you get into cycles, you're never going to find a solution. All right. So what we want to do now is try to figure out ways that we can do better than those uninformed search techniques. So some of the ways that we can do better are to avoid repeated states, as we say, and often if you do any kind of graph search, you'll have things like keeping track of your visited nodes, so that if you go there, you don't go back to it or regenerate it again. And the other one, and this is the one we're really going to focus on, which is this knowledge of trying to use anything that you know about the domain to prune and narrow down the search that you're going to do. So as I said, one thing you do is do not regenerate your state. If you've been there, if you do come back to that state, if you got there in a cheaper way than you got before, then you're going to have to update that path. We'll talk a little bit about that later. And the other one is this idea of keeping the visited node list. And you said, oh, I've been here before, don't generate it again. So here, now let's focus on heuristics. And the idea of the heuristics here is really what you're trying to say is every time you expand a node, you're hoping in the search, you're hoping that that's going to lead you, this is going to be it. This is like me in school. Yeah, this is the one that's finally going to reveal the answer to me, right? And of course, I have to go to another generation and another generation. But I'm hoping that I'm going down the right path, not all the stunted paths that I usually do. Heuristic is going to be a reflective of something that I think is going to be a promising path to expand. They're often either sort of metaphorically or actual distances from the goal. In the case of the moves, that's you're saying how many moves you'd have to do in the 8 puzzle to get to that goal. Or if you're in some kind of pathfinding, minimizing distance, you're trying to say how far it is I would have to go. And so you're trying to do estimates about that. And the closer you are on your estimates, the more likely the quicker you'll converge to a solution. And like I said, in the blind search techniques, there weren't a lot of ways to inform your search other than say, oh, I can generate these states because I know that about the physical things. I can only move the space so many ways. So you don't get a lot of ways to do this. So heuristics are going to guide which nodes and which trees we're going to expand. So some types of heuristics that we've seen, I think Zico talked about them, I talked a little bit about them. You have Euclidean distance, which is an obvious one. If you're doing like traveling or trying to minimize your distance to a route, One of the easiest ones to use is say, I'm going to ignore the roads. Right? I'm just going to ignore the roads, and I'm just going to say, what's the shortest distance from me to that location? And I'll say, that way, the frontier that I'm moving is I'm trying to get always closer by that as the crow flies, with that straight line distance. One thing to remember about Euclidean distance is that when you're doing world things, the world's not flat. So just something to remember. This is just a digression here. The world is not flat, so they have other ways of doing approximations, great circle approximations, and different ways to do that. And so you just have to remember that because it's a little bit different. Okay, as you imagine, in a really small, like if you're just doing Pittsburgh, it doesn't matter because you don't have much of the curvature of the Earth. But as I said, often when you're doing distance things, you do have to worry about that. The 8 puzzle or the 15 puzzle, there are things like the Manhattan distance and the number of misplaced dials. We'll go into a little bit more about that. Manhattan distance is just, imagine you being in Manhattan and you have to figure out how far to go. You can't cut through the blocks, so you have to go along the avenues and the streets. And so it's the distance from that you would travel on that piece. The number of dials, misplaced dials, is simply how many tiles are in the right place and how many tiles are in the wrong place, and the misplaced ones are in the wrong place. Traveling salesman person problem, you can construct this data structure. I'm not going to go into great detail about it, which is the minimum span tree, and there's a very fast algorithm for determining that, and that can guide which expansions you want to do next if you're starting from one location. If you're trying to figure out what's the way to get around and minimize the distance for that traveling salesperson problem. So this will, if you end up in search and doing your research in search, this will often plague you for the rest of your research. So just get used to this question. So one of the issues here is, how do you find heuristics? And then as we go on and we talk about different search techniques that we're going to do here, you'll realize that you want certain properties to hold for those search routines and for those heuristics. And the problem is that it's one thing to think about the intuitive thing about what heuristic I would apply to guide me in my search. It's another thing, can I get that to abide by these properties that I need in order that the search routines will work more efficiently? Okay. So often what we do when we do search, when we're trying to figure out a heuristic, is we try to figure out there's a really complex problem, and then there's sort of like, that's the problem I want to solve, and I'm not sure exactly what the curvature and how that search space is going to go, but I can talk about it in a simplistic way, relax the model so that it makes it easier for me to determine it. So by saying, I'm going to ignore the roads, right? I'm going to ignore the roads and just take the direct path. That means I've simplified the problem in the way I'm thinking about it. I'm just going to think, I'm not going to worry about all the different pathways I can get to a place. I'm just going to worry about going straight. And then by doing that, I'm making a heuristic that's working on the relaxed model, but I'm going to use that to guide to go through the actual model, which is I'm trying to figure out what's the shortest path to get from one location to another location. This is something that just to remember is that if you remember that you're doing these heuristics you're going to apply that to each of the states that you expand. If the actual effort of computing the heuristic is more expensive than the search, then you don't get any benefit. You're getting a negative effect, right? And believe it or not, you'll see this often. I mean, I've reviewed a number of papers where people will talk about the complexity and how they do all these things, and they say, look, we're just using the heuristic search to do this. And then you look at the computation and the complexity of doing the actual heuristic computation, and you realize it's dwarfing the search. So you have to understand that you can't use this incredibly complex way to get this great value only because it's going to be more expensive than the actual search itself. All right, so let me just talk about this. We've seen this in various forms, even in the uninformed search. But this is just sort of a very general form of a search algorithm that will then sort of augment as we talk about the different models that they use. And this general thing is very much similar like we've seen in uninformed, but it's in this form. You'll see this in the Russell Norvig book, and so I'm just presenting it so it's familiar to you as you see it. They call it a best first search. The idea here is that you have this open list, which is the nodes that you've expanded that you have yet to look into and to see whether they have solutions. And there are open ones that you're looking at. So when you initially start a search, it'll be the initial state you're in. Whatever the initial state you're in, you have this node, and that node is going to have is going to be on the open list, and that state of that node is going to be that initial state. that the problem started in. So in that 8 puzzle, whatever the configuration of that 8 puzzle is, that you're starting with, that would be the initial state. So you have this open list, and then what you want to do is you want to basically look at that open list. You're going to select the best node on that open list, and that's going to be based on an evaluation function that's applied to each one of the states of those nodes. And then you want to generate successor, and then for each of the successors, you want to, if it has not been generated before, this is the, make sure you don't have cycles or circularity, evaluate it and add it to the open and record it to its parent. So the only reason you record it to its parent so that you can recall the path that you needed to get there. So the idea here is that now we keep expanding nodes, we put them on the open list, we look at the open list, we evaluate each of those nodes, establish values based on that. The evaluation is going to be based on some heuristic function or some function that we're applying to it. And then we're going to select the best value, however we define the best value, whether that's a maximized value or a minimized value. And then we're going to choose that to be the next expansion. Each time we're checking, each time we look at it, is this a successful, is this the goal? If my 8 puzzle is in that state that I want, then I've got a solution. Otherwise, I'm going to go ahead, find the best one, expand, and look again. So here's one of the first easy ones, and this is what's called greedy best first search. And what greedy basically means is, have you guys heard the term greedy before? Yeah, so you are all pretty familiar with it. Basically, it means that you're going to look at some local set of things and make a selection based on that local set, not some global optimal. The evaluation of each of the nodes is, this is a heuristic, and you're going to say, oh, apply that to that state of that node and get a value, and then you're going to select the next node on the open list that has the minimum value, and then expand that until n is either the goal of h is 0 or you fail. Can't expand anymore. So here's an example of that you'll see also in the book. And forgive me, I even have a colleague who's Romanian, and I'm going to butcher the names of these cities. I can guarantee it. But nevertheless, I apologize for that. But nevertheless, this is a city of Romanian cities, and we're looking at this is your basic graph, and these show the distances to each one of these things. And you might have a question that says, what's the shortest distance from Arad to Bucharest? All right, and so you want to try to figure out how to get that. And so let's take a look at what some of that expansion is. So the first thing we want to do is we want to say, well, I want to be able to have a decent heuristic for this. So the decent heuristic, as I said before, is a straight line distance, Euclidean distance. And here I'm just giving you a table that demonstrates sort of what the straight line distances are from each of the locations to Bucharest. And naturally, if you notice, of course, to go to Bucharest is going to be 0. And so these are the straight line distances, not to be confused with these, which are the actual route distances to each of the cities. Okay? So this is the straight line distance. This is the heuristic values that we're going to use to guide our search. And now let's talk about expanding this out. So if you start off with a rod, and it says it's 366, as you saw back here, the distance straight from Bucharest, from Rod to Bucharest is 366. So you see that starts off at 366 here. So we expand this state, and we see directly on that graph, these are the ones that are the contiguous cities on the graph to it. And this one has a direct line of 253. This is 329. This says 374. These are all on the open list. We're going to pick the one that has the lowest value for that heuristic, and we're going to expand the, and I'm Sibiu, or I'm not sure. Sorry, apologize. So anyhow, so we come down here and we expand that out, and again we look here and we expand these out here, and all these values, 374, 329, 193, 380, 176, 366, they're all those nodes are on the open list. We're going to pick the minimum one again, which is going to be this Fagras. And we get down to Fagras, we go down here, we get 253, and look, lo and behold, we got our goal state. So this gave us a path to it. It's greedy, so it's not necessarily the optimal path to it. But it gave us a path. So the space complexity of the best first search is essentially the exponential in the, if you have to expand to all states, it's going to be exponential in the search space, state space, and it's also going to be, you have to keep all the nodes in memory if you have to keep the whole frontier. So again, it's going to be exponential. So there's a high space complexity to this. This is not going to solve all the problems if things rapidly expand. So you're going to look for ways to reduce some of that usage. A good heuristic will, in the worst case, they're still going to be exponential. But if you have a good heuristic, most of the time, on average, you won't get into those situations. So you're going to have something like that, and that's what a good heuristic is going to buy you. It's not going to solve the, this big exponential problem. But in most cases, it's going to be able to get you into a good place. And then you're going to have some termination, either time on computation, if you can't do it, because you don't want to run into that huge, huge exponential space. OK. So what I showed you was a greedy one, but what we haven't shown you is sort of this optimizing one. So one of the most popular search algorithms that you see in AI, and one that you will see countless different sort of renditions of and versions of. But it started off with something called A1, and then A2, and then rapidly became this A* algorithm, is the A* algorithm. And what A* attempts to do, or actually does a decent job of doing, is it is giving you guiding your search not just simply by how far you are from your current state to where you want to go to your goal. It's also taking into account how long it took you to get there. So it's trying to give you a total path cost, both what you've done to get there, plus the cost it's going to take you to the expected cost to get there. And if you optimize on that whole cost, then that will give you an optimal answer. All right. So here's what they do. They call this the function of n. They often call it the fat function. G is the cost that it took you to get there to a particular state. So if you're at some node and you apply this to it, this would simply be the cost that it actually took you. If you're looking at the graph like we were showing before, it would be the actual summation of the distances it took you on that graph to get to that particular city. And then H would be something like the straight line from that city to go to the goal city. This will show you, that straight line distance. And the total function, evaluation for the node, is this summation here. And what that will give you is that's the value that you're going to use then for selecting which node to expand next. And with A*, you typically formulate the heuristics and everything so that you're always doing it, picking the minimum value. So in the distance, you're saying which is the shortest distance I'm doing that, and that's how you formulate it. All right. So there are, in order for A* to work optimally, there are some restrictions that you need to put on the heuristic that you choose. It has to have certain kinds of properties. The first one is it has to be admissible. And by admissible means that it will never overestimate the distance to the goal from the current node. So if you notice the straight line distance, for example, is going to be admissible in that because of the triangle inequality, right? There's no way that you're going to get a shorter distance than that from point to point. This one, the monotone heuristic, or you also heard it as consistency, means that it's going to be monotonic, that the cost will never decrease along the path. So it won't be like, oh, I went to this node and the cost was 55, and then a next node that gets me to the solution, the cost then becomes 60, and then it goes down to 40. You're not going to have it. It'll always be constantly equal or less. Okay. So when H is admissible and monotonicity can be obtained when combined with the Pax max, this is just simply a trick that says, given a successor node, if you're getting a value of it, make sure it's either the max of the previous node, whatever the evaluation function was, or what the new value is for this value. So it's just simply a trick to maintain monotonicity. But one of the disadvantages of this is, remember what I said earlier, what you really want is a heuristic that gets you as close to the goal as possible. gives you the most accurate value what the cost is from a current node to a goal state. And this can, might give you a very coarse notion of that. So just remember that as you pick good heuristics, you can come up with values that you can maintain a monotonicity, but at the cost of having a very sort of not very accurate heuristic. All right, so let's go ahead again and look at the same search that we just did using the greedy best first, and now let's do A star. So A star, we come up here and we look at it. Remember that it was 366 as the bird flies from Arad to Bucharest, and so that means that the G value in the f of n equation that we saw is going to be 0 because we started there. And 366 is the value to the goal. So then we come down and we expand that here, and we see, like it says right here, 140 is the cost. That's going to be what the weight of that link is from Arad to Sibiu. And 254 is the estimate of the straight line distance from Sibiu to Bucharest. Okay, so it's the same thing here. 118 is going to represent, if I go back to the map, that's going to be the link, right? The edge on the graph that goes from Arad to Timisoara, and 329 is the heuristic value that we saw before. So all those values come up with things. We add them all up. We look and say, oh, here's the minimum one on the open list, so we're going to expand Sibiu, and we do the same thing again. And so each one of these values, these are the cost. Remember, the cost, and the cost is going to be the value it took to get from Arad to Sibiu, and the cost to get from Sibiu back to Arad in this case, or back to go to Bucharest. So it's the summation of all those values it took you to get to that particular node. So you do all that, and again, you have all these open nodes here, and from those open nodes, we're going to pick the smallest one to expand next. So we go ahead and do that, and we expand, and we look here, and we say, oh, 193, let's see what we have here. We have 646, 415, 671, 413, 447, 449. So 413 is the minimum one. So we go ahead and expand this node. We expand this node, we calculate the f of n for each one of these nodes, and we continue. Okay, so as we expand, we see we had, I forget what this one was. I think this was like 413, is that right, or something? Let's go back here. So this one's 415. So then we came back here, we come down here, 417 is the highest. Now this one, which was 415, is now the lowest of the one on the open list. We go ahead and expand that, we look here, and sure enough we found the Bucharest. But 450 is, we found it here, but we may not be the shortest solution. So we look again at the open values here, and 417 is still the smallest here now. So we expand 417, because these are all on the open list. We expand that out. And here we are, 418, we find a solution. 418 is the minimum one left on the open list. This is going to be the minimum path. All right. Yes?
You have to calculate Arad again when you come from there.
Right. So that could have been something that you could have cut off and not. So when you were generating the successors here, you could say in your generated successors, don't generate the one I was just directly back to. Notice that helps you sort of in the local, but it doesn't help you with cycles. Right. So if you had a path that went like this, you wouldn't know. You'd have to keep, like I said earlier, like a hash table or something around and said, I visited that node before. So it helps you in the minimum and it's sort of narrow thing. Yeah?
So wouldn't you be racking up a path cost if you're...
You would. The difference is it's possible to go in some search spaces, if you go back a little bit, if you can't find a solution and you go back, you can get in a cycle because you're not finding the solution. So if you can maintain that, then you're going to end up in some infinite loop, and you're not going to get a solution to that. So this is one of the ways to do that. Other ones, in certain graph situations, if you don't have the consistency property on your heuristic, then you may actually be able to get to a path with a lesser cost. And then you want to update that cost, and so that becomes a more favorable path. But if you can keep those properties in line, that's admissible and that's consistent, then you're not going to fall into, you don't have to keep this kind of closed list around. But you're right, it's going to it'll be very expensive. But all I was trying to say is that it is possible in some domains that you've come back around, and if that happens, so the obvious one of the short, but in some ways it's a very easy one, but it's not. But it doesn't help you with the longer range cycles. All right, so here's another example of A star, and in this case we're going back to our 8 puzzle, not because it's a particularly stimulating problem, but it's easy to show things on it. And the ideal here is I wanted to show a little bit about 2 different heuristics that you might use. And the 2 different heuristics, as I met earlier, are one is misplaced tiles, and another one is the Manhattan distance. All right? So let's look at the misplaced tiles. In the misplaced tiles one here, if you're using that, you start off with your initial node. You have that node in the open list. You look at it, and now you're getting the H value in that. The H value in that is going to be exactly the misplaced tiles, which is 4. And the cost of the moves that you took to get to that state, well, it's the initial state, so you didn't do anything to get there. So the f of n of that state is just simply 4. That makes sense? That's how you start your problem. So now we're going to go on and we're going to start expanding our states. So how do you expand the states? So here's sort of the answer. Some ways you could do this is that you could say, all right, I'm going to move the space any legal number of ways. I can move it to the left, I can move it up, I can move it to the right. I can't move it down, that's illegal. So that's my successor function. One of the things is, so anyhow, so we're going to do this, and so we move it here, we move the space to the right, we move the space up, and we move, I guess we move the space right here and move the space left here, sorry. So now let's look at the cost of those things and what the evaluation of those functions are, those states are. So here we have 5 tiles out of place. Here we have 3 tiles out of place, and here we have 5 tiles out of place. The f of n is 6, 4, and 6, okay? And the reason that is because you have the misplaced tiles, 5, 5, and 3, right? Plus the cost it took you to get to that state. And that was 1 move. So that's why each one of these is more than that, all right? So that's how you get to the evaluation functions for those states. All right, so we go down here. We have 3 misplaced tiles, 3, 3, and 4. And again, now it took 2 steps to get down here, right? We had to do 2 moves to get down here. So it's the 3 plus the 2 moves to get down here. Same thing here, same thing here. Okay, and more of the same as we come down here. Notice that we're always expanding the one that is the minimum value. In this case, where they are equal, just by, if you think of it as a queue, this kind of left to right on the queue, and so we are expanding the leftmost in the case of ties. And then we expand down here, expand down here. These are the smallest is down here, 5, and this is the goal state that we were shooting. All right. So notice how many nodes were expanded here, right? This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 nodes were expanded. Okay, and that's a nice way to look at things because that gives you a sense of the cost, the computational cost for finding the solution. And that's a good way of evaluating how well the heuristic is performing in the A star. So now let's look over here. Here, I'm just going to go through one board because it's not that interesting, and it's also too hard to show, what the cost would be. If you look at it, you're trying to figure out what the heuristic cost of the Manhattan distance of the tiles being out of place, you're just saying, all right, is the tile in the right place? If it's not, how many Manhattan distance, how many blocks would I have to move in order to get that tile into the right place? And then you just sum up all those tiles. All right, so one is, if you think this is the goal state down here, one up there is going to be one tile away, right? One tile away. 2 is going to be one tile away. 8 is going to be, you have to go down and over or over and down, so that's going to be 2 tiles away, right? 3 is in the right place, 4 is in the right place, 5 is in the right place. 6 would have to go down 1 tile, and 7 is in the right place. And so that's how you would calculate. So there's 5, that would be the 5 would be the total Manhattan distance out of place. Again, 7 is the number of misplaced plus the cost it took you to get down there, which is simply 1 in this case, because each time it's just 1 move. And we go down through all this thing, always picking the smallest, minimum 1 to expand, and we get down to here. All right? So everybody sees it's the same, it's exactly the same search, just using different heuristics to guide the search, which one's going to expand. Look at how many nodes are expanded here. 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So which heuristic performed better? Right, the one that has fewer expansions. Okay. So the way to think of A star as being, why is it optimal? Okay, there's sort of this intuitive and there's sort of an informal, quasi-formal proof for it. The intuitive explanation is that H is always going to be this lower bound because it's going to be, it has to be admissible. So it's going to be a lower bound. And F is a lower bound of the shortest path through that node because F is simply going to be the cost it took you to get there plus the H value to get there. F never decreases. So if F never decreases, then we're guaranteed that we're not going to be looping around. It's obvious from the first solution found is optimal as long as the solution is accepted when the cost of the solution is less than every other node that's on that node. And that's sort of just the intuition of it. Here's a little bit, as I said, quasi-formal proof about it. The idea here is that suppose there's a path cost to the optimal solution is F star. Let S of O be a suboptimal goal state that the path cost to get to that solution is going to be greater than F of star because it's suboptimal, right? Okay, suppose that A star terminates the search with S of O. So it means A star did not find the optimal solution. All right, so then let N be the leaf node on the optimal path O. If that's true, then the optimal cost has to be greater or equal to whatever the F of N is because of the admissibility of it. Remember, the admissible heuristic has to always underestimate or be exactly what the target can never overestimate. So that's true. And F of N has to be greater or equal to S of O because S of O was selected. Remember when we were always picking the minimal one. So F of S of O got selected for expansion, not F of N. All right, so we know that F star is going to be greater than F of N, and we know F of N is going to be greater or equal to F S of O from these statements. All right, so then we know that F of S of O is going to be exactly G of S of O because when you're at the goal state, the heuristic is going to give you 0 value. So the cost to get there is exactly what G is of it. Okay, but if that's the case, then F of star, because of this equation, is going to be a greater or equal to G of S of O. And that can't be because this is the optimal path. All right, so that's the proof that this is going to be optimal if those heuristic properties hold of monotonicity and admissible. Yeah.
Can we go down the suboptimal path if there is a tie and it was one randomly?
You can go down you'll do that as you even saw in an example before, but you will back up eventually because your cost will be low. Will be when you get down to here, right? You'll end up bottoming out, and you'll still have open nodes, and you're going to look at the next open node, which is going to be there. So A star is complete if there are infinitely many nodes with f of n less than f of star. Right, unless there are. I was confused by saying that. Unless there are infinitely many nodes, meaning that if you keep going and you have you can keep expanding states, and you have a function in your cycle or whatever, then you're not going to find the answer. But otherwise, you will find an answer. A star is complete when there's a positive lower bound on the cost of the operators, and the branching factor is finite. So basically, if the problem remains finite and you expand finitely, you're going to find an answer. So it's very powerful in that sense. But it has some disadvantages. You know, it seems like a great solution, and the big problem is that it has a huge space requirement. Okay. One more last thing about it is that for a given heuristic function, no optimal algorithm is guaranteed to do less work. That means this is maximally efficient. It's only going to expand the nodes that it has to for a given heuristic. So that means that it's doing the minimum amount of work it has to do for a given heuristic. But some heuristics perform better than other heuristics. So, which will result in less work if it performs better. Okay. So let's talk about measuring the heuristic payoff, because I've talked about that a little bit. I've shown a little bit. We talked about the expansions of states when we showed the 8 puzzle and the 2 different heuristic we compared. And here's this notion: is the you can look at basically the expansions of state. You have this notion that the branching factor for B star is going to be 1, and then it's going to be whatever the branching factor is as you go down the tree, and so on exponentially down, because you're expanding off of each one of those things on average. So that's typical just graph growth, or tree growth. So then we talk about this domination of heuristic functions. If you had 2 heuristic functions, and these are just the depths that you might find solutions. Imagine running this empirically, and we have different sets of problems, and we're going to just try to figure out which heuristic function works best for that domain of problem, given multiple instances of that problem. And we just come up with a table like this. And this shows you solutions that you might find at 2 or 6 or 10 or 14 or 18, the depth of the tree that you're looking at. And then you're looking at the number of expansions that it had to do to find those solutions. Which one of these things would you say is performing better? Which heuristic? H2. Right. So H2 is going to perform better in this case. So the idea here is because you're doing fewer extensions, it's doing less work, and being more efficient. One way to think about this is that if H2 is doing better, that means it's probably getting closer with its estimate. It's a better estimate about how far away a state is from the goal state. And the idea here is that if you get right on it, then you can't do any better. But as you said, you can't go over it because of the admissibility requirement. So the intuition here is that the higher the value is that you get without going over, the better that heuristic is going to be. Okay. So here we go into some of the issues with it. Worst case, you have to expand the whole tree. And the exponential, unless the error in the heuristic function is less than equal to the logarithm of the actual path cost, meaning the difference between the actual cost to get from a state to the solution versus what you estimated in your heuristic value. If that error is not less than the logarithm of the actual cost to get down there, then it can be exponential, exploring the whole tree, so it can be bad. This is the real killer in most cases, is because you have to be able to keep track of all the nodes that are in the open list, and if you don't have a heuristic that you can guarantee all the properties on, you have to do the closed list also. You can potentially have an exponential number of nodes that you have to keep in memory, and that will severely limit what you can solve. All right? These are the worst cases. In lots and lots of problems you do, you don't get them because your heuristics buy you that thing, and you will terminate that with some time limit that you put on how long you will compute something. But if you need a guarantee that you will get a solution, you have to do some other things to get those guarantees. Excuse me. All right, so given that we have this kind of a problem with memory and time, but particularly with memory, people have come up with algorithms for determining how to compute these things given a restricted memory space and how to restrict that memory. So some of the popular ones are IDA star, SMA star, and recursive breadth first search. Okay, so let's go into them. If you recall, iterative deepening was this notion when this is the uninformed search, where we just did depth first search, but we did it repeatedly with different depths that were allowed, right? So we could start off with 2 and then go down to 3, and it would look at all the space, and if it couldn't find a solution, it would increase the depth and look down at all the other space and see if it could find a solution, and keep doing that until it found a solution. The advantage of that is that it would only have to keep the depth of that at one time would just be the depth of that path of each one, and not all the nodes. This is very similar. You're going to do a depth first search like that, but instead of using the depth of the search, you're going to use this f bound, which is equal to the f value of the initial state, form a depth first search, and bounded by the f bound instead of depth bound. So the ideal here is that you, as you're expanding your tree, you have an f bound, and as soon as that f bound is simply the you look at the successors, find the f value for each one of the successors, and you find the minimum one of that, and that becomes the next f bound. And then you go ahead and search, and you find the next f bound and minimum of that. If you can't find a solution, then you go ahead and increase that f bound again. And then you look at all the different solutions within those f bounds. And so this is just doing iterative search, depth first search, but instead you're using the f bound as the limiter instead of the depth of the tree. And you get that f bound by finding the next lowest value of the successors. Previous search extends the previous bound, right? So that has the advantage of that you're using this depth first search with the f cost limit instead of depth limit, not keeping all the nodes in memory. The disadvantage is that you have to re-expand all these nodes all the time. So it's less efficient in that way, but it uses less space. Yeah?
Why is space complexity more critical than time complexity?
It's not, the thing about it is that you might find a solution if you have a really bushy tree, right? You might find a solution in a fair amount of time, but you're still maintaining all these nodes that have to be open. So you still, it's not that much worse. I mean, yes, the time complexity is a problem, but your space, you have to keep a lot of the space open before you ever even search these other places. So you will hit that barrier first, if you have that problem. But of course, it depends on where you're running it. In the environment that you're running it in, if you have real-time requirements, then naturally the runtime complexity is going to be more of a problem. All I'm saying is that a lot of these things are focused on doing space because they can't do a lot about the time ones. So they're focusing on the space ones. One of the things to think about now, even though a lot of these algorithms were developed when memory was not quite as expansive as it is now, but understand, even with the expansive memory we have now, it takes nothing in exponential time to use up all your memory. It just takes nothing. So don't be like, oh, I got gigabytes, I can do all this stuff. It takes nothing. It's a chump change. It just goes away. So that's not going to work very much. So you really don't want to go into that exponential world in that place. Also, another place to think about that is in embedded systems. You don't have a huge amount of memory. So you still have those kind of memory restriction things. And more you're going to see embedded structures. You see in robotics. You see it in all kinds of actuated and situated systems. So another algorithm that, again, is focusing on the space complexity and how to do it, how to reduce it in a reduced space, is this SMA star. There's actually an MA star, which is it's a generalized version of this. It's more complicated. You can look it up on your own, but I just wanted the more straightforward one is this SMA star. Believe it or not, the S stands for simple. So anyhow, The idea here is to use whatever memory is available. So you start off the search saying, I have enough memory for X number of nodes that I can keep my memory. Whatever. You start off with that restriction automatically. Complete with available memory is sufficient to store the shallowest solution path, meaning that if you can store up to 8 nodes, but your solution path is 9, you're never going to find the solution that's 9 length. It's only complete up to the point that you can store that solution path. Returns the best solution that can be reached with available memory. It's guaranteed to do that. Optimal if enough memory is available to store the shallowest optimal solution path. Again, it's just not, it makes sense. If you don't have enough memory to store those paths, then you're not going to find the solutions. And it's optimally efficient when enough memory is available for the entire search tree. All right, so let's take a look at SMA star and see how this works. So here's a simple search tree again, we start off with the initial state, and this is some heuristic value of 12. And so the F value for A is going to be 12 here. And this just shows you the whole tree. And the reason I'm showing you the whole tree is then I'll show you how SMA is going to be applied to this tree in a memory restricted way. All right, so again, you can see these things, 10, 10 down here. Here, the ones that are in squares here are solutions. So 20 is a solution, 30 is a solution. These are all goal state and found. All right. Now let's take a look at SMA star and how it might be applied. In this particular instantiation of applying SMA star, we're assuming that we have enough memory for 3 nodes. Okay? So then we say here it starts off with 12. We're expanding A. Remember, we have B and G as the children of that. So we say B and G. And notice now we have no more memory for any nodes. So we have to do something to recover that. So what happens is that it will look at this and it will say, all right, this one is the highest expensive one, right? So we annotate this node up here saying the next best one is 15. The next best one of these is 15, all right? And now we've freed up this memory, gotten rid of that node, and we now can expand out on this one. So we expand this one out here. This says, is this a solution? This is 18, but is it a solution? It's not. I can't go any deeper to this, so I'm just going to mark this as infinite. So I'll never look at that again, right? So now I'm going to free up this again. I'm going to free this up again. Notice the alternative is infinite because we made that an infinite here. So I free that up, and I look here, and I got 24. It is a goal state, so I mark this as 24, saying this is a solution. But it may not be the best solution, right? So we're going to look back, okay? So now we go back and we say, oh, 24 is greater than 15. So now I'm going to go back here and look at 15, all right? So that means I have to get rid of this node, but that's okay. And I expand out this B, and I get to 15. And I said, all right, I've used up all my memory again. So I annotate back here, and I say, well, I found a solution at 24 over here. And I freed up that memory for this one. And I look over here, and I say 25. It's not a goal state. I've used up all my memory. Therefore, it's I'm going to mark it as infinite. Okay? Okay, and so once I mark this as infinite, I'm going to free this up, and I'm going to now look at the other child underneath B, which was 20. 20 is a goal state. Notice the alternative here is infinite, so it's a goal state here. 20 is better than 24, and so this is my state here because I can't expand anymore. And there's no, and it's already beating the other alternative, which was 24. And so here I've found all the solutions, the optimal within 3 nodes, 3 steps. And so that gives you a way of giving solutions given your memory restrictions. If the solution didn't fall in there, you might have found a solution, but if the optimal solution didn't fall in that, and it was a longer path, you would not have gotten it. So that's the sacrifice you make using these kind of approaches. It may be that a solution is 8 nodes away, you wouldn't have found it. And it would have come back with, I didn't find a solution. But meanwhile, it was a way of sort of limiting and curtailing your search to the amount of space that you have available within your processor. Okay. Yeah, we can do this. Recursive best first search. So recursive best first search is this notion of remembering, again, similar to SMA star, remembering what the alternatives are, and then only keeping a notation of that memory of what the next best one is, and then regenerating it when you come back to search it. And I'll show an example of this. But the idea here is that you start off as the initial state of the problem, and then you start off with some basically like a threshold there, and you start off initially infinite, has no bound. And then you call this recursive best first, and it says, if you look at the node and it's in the goal state, beautiful, return that goal state. All right. Otherwise, expand the successors, and then if the successors are empty, meaning that you can't generate this one, then you return failure from that particular invocation of the RBFS, and return back an infinite value for it. And then for each of the successors, figure out the f of value for each of the nodes. And notice that this is doing this max of GS and f of node, which is simply that path max that we saw earlier, a way to make and guarantee the monotonicity of the heuristic. Okay. And then you repeat here. You find the lowest value f value node in the successors. That's the best node. That's the lowest value. If its best is better than the limit that's passed down, then return failure, because that means you've reached your threshold and you want to cut off. Otherwise, you want to find what the next best one is. And this is the one that if you fail, then if you ever come back to this, this is where you're going to start your search. Okay? And then you're going to recursively call it again here with the problem, the best node where you started from, and this is just the minimum of whatever the f limit is and the alternative. And you keep going down for that indication of it. I'll show you how this expands in a second, so it's a little bit easier to follow. But this is just a sort of a structured straw representation of the algorithm. So let's go back to our cities again here. And we're again going to try to see what's the way to find from going from Arad to Bucharest. All right? Okay. And here we have the expansion here. We start off with Arad being on infinite, and 366 is the f value, is the cost for the heuristic value to go straight to it. We expand out. If you look here, we're going to expand. The minimum one that we're expanding out is 393, but the alternative, the next best alternative, is 447 here. So we annotate it with the 447. Okay. And we expand this out here. We expand this all the way out here. Again, we get down to here. The next best alternative is the 415. So we annotate that out. And now we're going to recurse down here. And we get down here, and we get these children. Notice now 417 is going to be greater than 415. So now we stop this search here. We mark it back up here. We collapse this, get rid of those nodes, put 417 by, because the recursion, we basically backtracked in there. Put 417 here, and now we're going to expand this. So now we're generating these again here. So we generate these two again. Okay. And as we go, we're switching. We look here. Let me go back here for a second. We look here. We expand it here. We have 450 here, which is going to be, now the lowest is back to 417. So now we're going to bandy back out there, and we have to again re-expand, because now we've backtracked, and now we're going to go back down. So now we're going to expand those nodes again. So we expand these nodes again. We see 417. 417 is the lowest of the ones available to us. And we go down here, and we look at these in here. Where's the 417? Okay. So we get down to the Bucharest here, and we find that the best solution in there. Okay. So that sounds good. I'm trying to figure out where I should go on. I'll just start with this. So we gave you now search algorithms for generatively finding solutions to problems that we are concerned with the order of steps. What path would we take to get from Marad to Bucharest? What set of moves would we make to get from a initial state to a goal? But there are types of problems where we don't care about how we get there. We just care about the end. What's the configuration? Right? So in the 8 queens problem we saw, we don't really care how we determined what the positions of the queens are on the board. What we care about is where they're on the board and if they're in the positions that will obey all the constraints that we've made for that, which i.e. no queen can attack another queen. Same kind of thing for any kind of configuration, VLSI design, computer configuration, job set scheduling. So all these things, you're just concerned about the ultimate configuration. You're not concerned about the steps you took to get there. So an approach that often works, that's a nice way to do these things, if you don't have a strong notion of the theory of the domain, are these local search algorithms. And the idea is basically you don't know what the solution is. You just know that you want, so for some things that you want to optimize versus satisfy. So the queen's problem can be a satisfaction problem in that as long as you don't have any queen attacking each other, you've satisfied the problem. Optimization is a little bit harder in the state that you want to get to a point where whatever you're trying to minimize can't get any better. All right? The idea of local search is that you basically can rapidly create a solution. And it may not be a solution that works, so you rapidly can come up with a state. I can create a state for the 8 queens problem. Just randomly put the queens on one in each column. And then I can say, is that a goal? No. If it's not, then I can do some manipulation on that and create some neighbors. And then I look at the neighbors and say, how's that neighbor compared to the one I'm looking at? If there's a neighbor that looks more promising, fewer queens in conflict with each other, then I'm going to explore that one and do it again. So it's this quick snapping from a total solution to another total solution. All right. So I realized that I had a Piazza poll that I did not run. So you guys lucked out today. Sorry about that. Anyhow, I'll keep going. I'm undoubtedly the most forgetful person in the world, so you should enjoy this. Not that you can come to me and say you forgot things. Anyhow, so some of the advantages of the local search are that it's very simple to implement, usually. If you can rapidly generate total solution states, then it's easy to implement. Still have the problem of saying what makes something better than something. Still have the problem of determining what's a good neighbor. Very little memory is needed. In fact, it's easily to bound because you can choose how many neighbors you want to keep around, right? And you can often find reasonable solutions in very large, somewhat continuous, not continuous the way that Zico was showing you, space, and for which systematic algorithms are not suitable. In fact, I think, would you say that wouldn't you say that some of the neural optimizations are kind of fall under local search?
Yeah, certainly for non-convex ones you want.
Yeah, that's exactly what I would say. Yeah, so these are not discrete. Yeah, it's not something separate. These things do fall in the same kind of categories. 250. Okay, so I'm not going to go into it. What we'll do is next time we'll start up with hill climbing, which is a very famous way, and there are different versions for it. And this is about how you try to get optimization. You get closer and closer to a solution, but you don't know what that solution is going to be.